Yeah, so I just have to repeat this in short a bit. Yeah, so I'm sorry, but I'm Shubhajit Das. I'm a PhD student in the Department of Mathematics at IISc, and we'll be solving category theory problems every week based on the material that is being done that in that particular week. So far, I have just sort of revised what a category is and given an example and some motivation behind why exactly we are doing this. But yeah, so these things have already been covered in your lecture course this week, but based on some requests, we are having a short recap of whatever is needed to solve the assignment problems. Okay, so an object I in a category C is an initial object of C if for every object A of C there exists a unique arrow or map or morphism. So unique map or morphism from I to A. This is what an initial object means. Being an initial object means. Dually, an object T in a category C is a terminal object of C if for every object A of C there exists a unique map A to T. This is what a terminal object is. And based on whatever we have discussed so far, you can understand that in the category top of topological spaces, what is your terminal object? Someone can answer. What is a terminal object in the category of topological spaces? We just discussed this, right? What is a terminal object? It is a particular object T which has this property that given any arbitrary object A of your category, there is a unique map from A to T. So if you look at the category top of topological spaces, what is a terminal object? It is the I'm audible, right?
Could you repeat the question?
Yeah, my question is if you consider the category top of topological spaces, what is a terminal object in that
That
category?
singleton and that
Yeah,
discrete
the
topology.
singleton space. The singleton space with its discrete or trivial topology which coincide actually. Right. So that is a terminal object. What is the initial object in that category?
Empty set.
Exactly. Empty space. In the category of groups, what is an initial object?
The identity.
The trivial group.
Yes,
You
the
shouldn't say
trivial.
identity because I mean, elements are not objects.
Yes,
Groups are
yes.
objects in that category. So, yeah, the trivial group is an initial object. What is a terminal object?
Except the trivial group itself.
Yeah, the trivial group again. Okay. Um, you guys know about fields, right?
Yes.
Okay. So what is so we'll consider the category of fields whose objects are fields and whose arrows are field maps, field homomorphisms. So what is an initial object in this category? I mean, does it exist?
In the field
In the
category.
category of fields, is there an initial object? Is there an initial field? So for an object in a category to be an initial object, what you need is that for every object A of the category, there should exist a unique map from your initial object to A. Now in the category of fields, so fields can have different characteristics, right? And you know that there is no map from a field of characteristic P to a field of characteristic, let's say Q, for some different prime Q, right?
Okay. Yes.
So that
So
means,
are we taking the if we take the characteristics 0, then we have only one field, right? So we
no,
have
not
taking the
necessarily. Q is a field of characteristic 0. C, complex numbers, is a
sorry.
field of characteristic 0. But my point is this, that if let's denote the category of fields by FLD, then then this Hom set FLD of F comma E, where F has characteristic P and E has characteristic Q, this is empty. There are no maps from F to E, right? This Hom set is
Yes.
empty, right? You agree, right?
Yes.
So that means that the category of fields cannot have an initial object, because if it has an initial object I, so a field I, that means for every field E, there should exist a unique map from I to E. But if E has characteristic different than I, then there is no map from I to E. Let alone, I mean, you don't even have a map in the first place. Okay. So you don't need to worry about many maps, but the issue here is that you don't have any map. There is no map from I to E. So the category of fields cannot have an initial object, and for the same reason, the category of fields does not have a terminal object. So we know what an initial object is, what a terminal object is. Good. And what else? Yeah, so we also need to quickly understand what an isomorphism in a category is. So as I said, think of the arrows of a category as maps in the category. So an arrow in a category is to be thought of as a map in the category. Now in group theory, you have learnt about what an isomorphism is, right? What is an isomorphism of groups? What is an isomorphism? Someone quickly tell me. This is very basic.
Homomorphism and bisection.
Yes, homomorphism and bijection. So an isomorphism is a homomorphism which is also a bijection. Right. So how do you define a bijection? How do you define a bijective map? You define it to be a map which is both injective as well as surjective, right? Now to define injectivity and surjectivity of a map, you need elements of your set, right? You define injectivity in this way. So a map F from A to B is, let's say, surjective if for every B in B there exists A in A, such that F of A is B. But in category theory, we don't have this such detail of elements, right? An object, as I said, is just a blob, just a dot, just a letter, just a symbol. There is no internal structure. So we don't have the have this detail of have this extra detail for which we can't really define what a bijective map in a category is. But there is an equivalent characterization of bijective maps, right? At least for sets you have seen, right? So a map F from A to B is bijective if and only if it is invertible, right? It has an inverse. That is, there exists a map G from B into A in the opposite direction as that of F, such that G composed F is identity on A and F composed G is identity on B. We know this, right? This is an entirely an external description of a bijective map, and this is what we will use to define an isomorphism in an abstract category. Okay, so let's quickly write the definition. An isomorphism, okay, so let's write it properly. An arrow, that is a morphism, that is a map, if from A to B in a category, is called an isomorphism if there exists an arrow G from B into A in the category. You should you want the existence of such a morphism G in the category, which serves as an inverse of F, such that G composed F is equal to 1A, F composed G is equal to 1B. Okay, simple. So I'll call a morphism F in a category to be an isomorphism if there exists a morphism G in the category in the opposite direction as that of F, such that G composed with F and F composed G are the identities. Okay. So tell me, okay, so first of all, this is a trivial exercise you have seen previously, or you can see in the lecture videos. I'm sure it has been done there, that if is, so if an arrow F is an isomorphism, so if a map F in a category is an isomorphism, then it has a unique inverse. Please check this. Okay, and the inverse by definition is again an isomorphism. So tell me, we'll just give write a table for different categories, and you'll tell me what are the various isomorphisms in those categories are. So category and isomorphisms in the category. So for example, the category set. What is an isomorphism in this category? So it should be first of all a morphism, and it should be an invertible one. So a morphism in set is just a set map. And what is an invertible set map? Someone please quickly tell me.
It should be bijective.
Yeah, exactly. So a bijective map. So the isomorphisms in the category of sets and mappings are precisely bijective maps. The category group. What is an isomorphism in this category? Yeah.
Homomorphism and bijection.
Which means an isomorphism in the usual sense of groups.
Yes.
So isomorphism of groups. Let's say the category top of topological spaces. What is an isomorphism in this category?
Bicontinuous maps.
Yes. Why? Yeah, very good. But why exactly? Why do you need the? Why do you need a bijective continuous map whose inverse is also continuous?
Because here the surjectivity is defined in terms of the inverse function. So it should be continuous in the one way and the other way around. The inverse should also be continuous.
Should also, I mean, there are also maps which are bijective and continuous, but their inverse, which exists because of the bijectivity, is not continuous.
Okay. Not continuous, yes.
But isomorphisms are only those which are bijective, continuous, and whose inverse is also continuous. So why exactly are we asking for the continuity of the inverse? It's because of the definition. So it says that an arrow F in a category is called an isomorphism if there exists an arrow G in the category. The arrow should also be in the category. The inverse arrow should also be in the category such that these two hold. So for the category of topological spaces, a map F from A to B, which is a continuous map from space A to space B, will be an isomorphism if and only if there exists a map G from B to A in the category of topological spaces. So a continuous map G from B to A such that G is an inverse of F. And that is why the isomorphisms are exactly homeomorphisms. What about the category of let's say differentiable manifolds? The objects, every object is a manifold. I mean, I understand the frustration of geometers here, because you are treating a manifold as a blob or a dot essentially. I mean, I understand people get frustrated, but yeah, that is how category theory is. So the objects are differentiable manifolds and the arrows in this category are smooth maps. So what is an
This
isomorphism?
should be diffeomorphisms.
Yeah, diffeomorphisms. Okay. To conclude this beginning discussion, we are already at the end of an hour, but to conclude, I would also like to mention categories in which the objects do not have underlying set structure. So in all these categories, the objects do have some set structure on them, but as we already mentioned that in category theory, there is no internal structure, right? And in particular, we defined an object to be a primitive notion in a category, right? So an object for us is a primitive notion. It's a letter, a symbol, a blob, a dot, whatever you like, right? It's just a primitive notion. There is no internal structure. So an object is a primitive notion. So we better give an example of a category in which an object is not a set. So let X be a partially ordered set. You guys know what a partially ordered set is, right? You guys know, right, what a partially ordered set is? A set X together with a binary relation on X, which is reflexive, antisymmetric, and transitive. Reflexive means that every little x in X is less than equal to little x. Antisymmetric means that if X is less than equal to Y and Y is less than equal to X, then X is equal to Y. And transitive, of course, means that if X is less than equal to Y, Y is less than equal to Z, then X will be less than equal to Z. So this is what a partially ordered set is. What we want is to construct a category out of this single partially ordered set. So we define our category as follows. Let's write this category as script X. So objects of script X are elements of X. So the objects of script X are now elements of the partially ordered set X. So you understand, objects do not have any, I mean here the objects are not sets themselves, right? They are just elements of some partially ordered set. And what about the Hom set? So the Hom set from an object little a, which is an element of X, to an object b, little b, which is an element of X, will be defined as follows. So it will be singleton, by which I mean there is exactly one arrow from A to B, whatever it is, if and only if A is less than equal to B, and this is defined to be empty otherwise. Okay. Now you can check that transitivity of the partial order imposes a unique composition law for composition of morphisms, and reflexivity of the partial order imposes the existence of identity arrows. So since the relation is reflexive, x, any little x is less than equal to little x, which means that the Hom set from little x to little x is singleton, which means that there exists an arrow from little x to little x, and by our definitions you can check that it will be the identity arrow. So as a concrete example, you can take this partially ordered set. For example, let's take 0 less than equal to 1 less than equal to 2. This is a partially ordered set of 3 elements. How would the associated underlying category look like? So the objects of your category will be elements of partially ordered set. So this is an object. We denote the object 0 by dot. This is the object 1. This is the object 2. These are your objects in your category. Note that the objects here are not sets, right? They are merely abstract. They are just elements of your partially ordered set. An object here is an element of your partially ordered set. So it can be anything abstract, as I mentioned, right? And what are the arrows? So from 0 to 1 there is an arrow because 0 less than equal to 1. From 1 to 2 there is an arrow because 1 less than equal to 2. From 0 to 2 there is an arrow because 0 will be less than equal to 2. And you have identity arrows. And that's all. There is no arrow from 1 to 0 by your definition because 1 is not less than equal to 0. Okay. This is an example. So this is an example of a category in which the objects are not sets. Okay. And that is why we always mention in the definition of a category that a category consists of a class of objects. That's all that we know about objects. Nowhere in the definition do we mention what an object should look like or what an object is. We don't mention it anywhere. We only talk about objects in the first point, and the only thing that we know from the definition about objects is that it has a class of objects. A category has a class of objects. So objects are being treated as a primitive notion, and anything and everything that you can think of is an object. A set may be an object, an element of a set may be an object, a theorem may be an object, a group may be an object, I don't know, an emotion may be an object, etc. Anything abstract that you can think of. And we just gave an example of an abstract category. Okay, so let's quickly start solving problems, otherwise we'll miss out. Okay, so let's go with the first one. Yeah, so an object Z of a category C is called a zero object if Z is both an initial as well as a terminal object of C. So Z has both initial object property as well as terminal object property. So for example, as we already saw in the category of groups, the trivial group has this property. It is both an initial object, it is also a terminal object. So it is a zero object. So you are being asked to state whether each of the following statements is true or false with brief justification. So first of all, the category set, which we have already seen previously, objects are sets, morphisms are set maps, usual composition identities, has a zero object. Is this true?
No.
No, right? Because we saw that the category set has an initial object, which is the empty set, and it has a terminal object, which is a singleton set. Of course, that doesn't mean that it cannot have a zero object. For that, you need to work a bit more and try to show something. So what exactly so how can you prove that it does not have a zero object?
By contradiction, probably.
Okay, so how would the argument go? That is what I'm asking. How would the argument go? So keep in mind that, so one of the main uses of doing category theory is to have a formal framework for defining what an universal property is. I'm sure most of the people here who have been studying mathematics have seen at least one example of universal property. For example, free group construction or tensor products, etc., etc. So one idea of category theory is to have a formal framework for defining or discussing universal properties. And initial objects, terminal objects are all universal objects. They have a universal property. Initial objects have this universal property that given any arbitrary object A, there is a unique arrow from the initial object to A. Terminal objects have this universal property that given any arbitrary object A, there is exactly one arrow from A to the terminal object. Right? That is, I mean, the names it's themselves suggest this. Something is initial means it is, I mean, it maps to everything in a unique way. Something is terminal means everything maps to it in a unique way. There is a unique map in both cases. Okay, so suppose let C be a category. Let I and I prime be initial objects. Can we say that there is an isomorphism from I to I prime? So if there is an isomorphism from one object to another object in the category, we call the two objects to be isomorphic and write it in this way. So basically, if there is an isomorphism from A to B, F, by the way, an isomorphism which we have already defined to be an arrow which is invertible is always denoted like this. So you write an arrow for the morphism, and since it has the iso property, the invertibility property, we'll decorate the arrow with a tilde. This is what an isomorphism is denoted by. So an ordinary arrow that is mapped in a category is just a simple arrow, let's say G. An isomorphism in your category will be an arrow decorated with a tilde. Oops. If let's say okay, so if there is an isomorphism from an object X to an object Y in a category, we say that X and Y are isomorphic, as we have seen for groups or rings, and we write X is isomorphic to Y. Okay, so yeah, tell me, suppose I and I prime are two initial objects of C. Is there an isomorphism from I to I prime? So I is an initial object, which means that for any object A, there is exactly one arrow from I to A, right? So in particular, I prime is an arbitrary object in your category. So that means there exists a unique arrow from I to I prime. Let's say this is F. Similarly, I prime is an initial object, right? So what can you say? What can you say about I prime as well?
There exists a unique arrow from I prime to I.
There is a unique arrow G from I prime to I. So this, the existence of the first arrow was by the universal property of I. So since I is initial. And this is since I prime is initial. So you can compose these arrows. So you can take the arrow G composed F, which is from I to I. Now again, I is an initial object, which means that for any arbitrary object A, there is a unique arrow from I to A. This in particular applies to the object I itself. So there should be a unique arrow from I to I itself, right? And we already know what that arrow is. Identity. So this should be equal to identity. Similarly, F composed G should also be equal to identity on I prime, which means that F is an isomorphism, which means that I is isomorphic to I prime. So any two initial objects of a category are isomorphic. Dually, any two terminal objects of a category are also isomorphic. Right. So I'll come to what dually means. It has been again been defined in this lecture this week, but I guess you guys might not know. But yeah, we'll come to that. So the category set has a zero object is a false statement. False, right? So okay, let's write it nicely. So A is false, right? If the category set has a zero object, let's say an object that is a set Z, then Z is in particular initial as object and Z is also terminal. We know that initial object in the category of sets is the empty set. So by our previous consideration that any two initial objects in a category should be isomorphic, Z should be isomorphic to the empty set, and Z is terminal means Z should be isomorphic to the singleton. Isomorphism is a transitive relation, which means that the empty set should be isomorphic to the singleton. Now what is an isomorphism in the category of sets? It's a bijection. So there should exist a bijection from the empty set to singleton. Does there exist a bijection? From empty set to singleton?
No.
Of course not. So this is your contradiction. Okay. Question B says the category group, which you have already introduced, has a zero object, and we know that this is a true statement. Is true. The trivial group is a zero object. Of the category of groups. Let's see what about C. Okay, so this is where we need to define what C op is. Duality, dual category is. So I'll quickly mention this. Okay. So this is, so taking an opposite is a way of constructing a new category from a given category. So think about what a category essentially is, or think about what the data of a category essentially is. It has objects, which are dots. It has maps, which are arrows. It has a composition. It has identities, subject to associativity and identity axioms. Now, formally speaking, a category therefore is just a directed graph, right? With extra structure, objects and arrows. Objects and arrows with extra structure, composition, identities, etc. So this is what a category is. This is what a category looks like, right? So you can.
So the objects need not have structure, but the category itself will have structure.
Structure of composition of arrows, yeah.
Okay.
You don't even need to mention objects need not have structure. I mean, there is no point in saying an object, because once you say it is an object, you treat it automatically as a primitive notion. Okay. So no need to even think about object having a structure. An object is just a dot for you. That's all. But yeah, I get your point. Yeah. So this is what a category essentially looks like. So formally speaking, you can of course ask, what if I flip all the arrows in the category? Right? What if I reverse the direction of every arrow in the category? Turns out that this is what is exactly called the opposite category construction. So let C be a category. The opposite category C op, also called the dual category, is defined as follows. So of course, objects are dots, they are blobs. There is no point in flipping an object. Doesn't make any sense. So objects of C op are the same as the objects of C. The objects are the same. The difference lies in the arrows. So for every ordered pair A comma B of objects of your category, so which are also objects in C op. So in C op we can say the home set in C op from the object A to the object B should be defined to be, what should we define it to be? You are just flipping arrows of C. So what should this be? This should be the, come on,
B to A
yeah,
arrows.
in C, right? So C is a category, C op is our new category. We want to define what C op is. So in particular, we want to define what a home set in C op is. And a home set in C op, in particular, the home set in C op from A to B is defined with the home set in C from B to A, right? So sometimes, so as to not confuse, I mean, so the usual, what this notation suggests is if F is an arrow from B to A in C, then in C op I will write the arrow F, I mean F will be an arrow from A to B. To avoid confusion, what people do is use op for the arrow, corresponding arrow in the opposite category. So the notation would be this, that if F is an arrow from B to A in C, any arrow, then the corresponding arrow in C op will be written as F op from A to B. Note that these are arrows in different categories. This is an arrow in the category C, while this is an arrow in the category C op, in the opposite category. Okay, this is how we will write arrows. So what essentially is C op? C op is just C but with the direction of the arrows reversed. That's all. The objects are the same, but the arrows of C are flipped to give you the category C op. Yeah.
So when you talk about the object, the arrows are reversed.
Yeah.
That means what is the relation between F and F op?
There is no relation. There is just a correspondence. So for every arrow F from object B to object A in C, there is an arrow F op from B to A. There is a corresponding arrow F op from B to A.
So there is no need to be any inverse type of relation with them.
Because these are arrows in different categories. You can't even combine them.
Okay.
Right. So essentially, instead of writing it like this, one can say that there is a one-to-one correspondence, or there is a bijection from C op A comma B to C B comma A, where an arrow F in C from B to A will correspond to an arrow F op from A to B in C op. Okay, you can also say that there is a bijection. You can either define it in this way, that the arrows are the same but with the direction reverse, or you can say that the arrows of C op are in one-to-one correspondence with the arrows of C. So an arrow F in C corresponds to an arrow F op in C op. You can say these things. Okay, and what else? Of course, we need a composition. We need to check that this is indeed a category. We need to define a composition. So suppose you take arrows A to B, F op, B to C, G op in C op. What I want is to compose them. What I want is to assign a third arrow in the category C op from A to C. So is there a natural composition? I mean, in other words, is there a natural way of defining this to be an arrow from A to C? What particular arrow should we take? Yeah, op is not appearing. Sorry?
F of G.
F compose G. But F compose G is in C, right?
Yes.
So we want an arrow in C op.
Okay, F of G of op.
Yes, exactly. So the idea is simply this: if these are two arrows in C op, then this correspond to arrows A, B, C. This is F, this is G in C. Now, of course, there is an arrow from C to A in C because C was a category. This arrow is exactly F compose G, which means that in C op you have this arrow from A to C, which is F compose G op in C op, right? So what we do is we define G op composed F op. The composition of C op is defined to be F compose G op. Simple, right? And what about identity arrows? So from any object A to itself, what should 1A in C op be? This is just, so let's write it. I mean, let's not use this notation right now. But yeah, my question is, what should the identity arrow from A to A be? This should exactly be the corresponding arrow of the identity arrow in C, right? Identity arrow in C op is exactly 1A op. So 1A was an arrow in C, right? From A to A, which means by our definition that 1A op is an arrow from A to A. We have flipped the arrow, but you can't see it because the domain object and the codomain object are the same in C op. Okay, and you can check that associativity, identity, everything holds, and this is what makes C op into a category. Sometimes people also like to write it as C star, but I don't prefer that notation. C op is the better notation. C op is called the opposite category or the dual category. There is a very infamous principle, a meta theorem in category theory called the duality principle, which says that suppose if you have a particular statement which holds in a particular category, then its dual statement, which is obtained by keeping the objects same, reversing the direction of all the arrows and changing the order of composition, this dual statement will be true in the opposite category. And you'll see many instances of this duality principle later on. But yeah, for now this is what the opposite category is. The opposite category is C op of a category C. Okay. Yeah.
So basically the identity in both the cases are same, right?
Yeah. Just you write 1A for identity in C, you write 1A op for the identity in C op.
We write it like that, but basically they should be the same.
Yeah, but I mean these are different categories, and that is why we introduce this op notation, right? So as to not get confused. So we are just following our convention. Every arrow in C op will be written as an arrow of C op. Okay, that is what we are following. So there is no particular way of comparing 1A and 1A op because these are in different categories. But yeah, essentially you can say that, I mean, it's just the formal flipping of the arrow, that's all. That is what you are doing. You are just only reversing the direction of the arrow, keeping the name same. So the point is C op is indeed a category which is called the opposite category of C. Okay, so let's quickly come to this. So the question says if C has a 0 object, then C op has a 0 object. What do you think? Is this true or false?
Not necessarily.
Okay. So let's quickly, now that we have understood what an opposite category is, let's quickly see this. Suppose C is a category with a terminal object. Yeah, let me see if the recording is still going on. Yeah. Terminal object. Suppose C is a category with a terminal object. Terminal object, let's say T. Question is okay, so question is T is also an, of course we know that the category C and the opposite category C have the same objects, so I can talk about T being an object of the category C op as well, right? So as an object of C op, what do you think T should be? As an object of C op, T is a dash object? What do you think this dash should be?
Initial.
Yes, exactly. That is why, that is what the point of taking opposite category. That is the point of taking the opposite category or the dual category. So if T is a terminal object in C, by this means that for every object A in C, there is a unique arrow from A to T in C. We claim that T will be an initial object in the category C op, right? So forget the category C for the time being. Just focus on the category C op, the opposite category. So look at the category C op. T is an object here. We want to show it is an initial object, which means that for any arbitrary object A, what we want is a unique arrow from T to A in C op. Now what actually guarantees that such a unique arrow exists? Because T was a terminal object in the opposite category C, we know that for this particular object A, there exists a unique arrow from A to T in C. Now as I already mentioned, the Hom set in C op from T to A is exactly defined to be in bijective correspondence with the Hom set in C from A to T, right? So if there is a unique arrow from A to T in C, there is a unique arrow from T to A in C op, right? And this happens for every A. So for every arbitrary object A, there is exactly one arrow from T to A in the opposite category C op, which means that T is exactly an initial object of the category C op. Understood? Did everyone understand this? Did you guys understand this? It's clear, right?
Yes, yes.
Similarly, if T is a T is an initial object of C, then T considered as an object of C of will be a terminal object. And that is why the property of being an initial object and the property of being a terminal object are dual notions of each other. Because if an object has one property in a category, then the object will have the dual property in the opposite category. Okay. And similarly, you will see many other duality notions, duality properties. So let's come back to this question. It says that if C has a zero object, then C up has a zero object. What do you think? So C has a zero object means that C has an object which is both an initial object as well as a terminal object. So what do you think? This should be true or false? What about C up?
Intuitively, it should be true.
Intuitively and mathematically as well, it should be true. And what is the argument exactly? If
Because it's bijective, like what was initial would be final.
yeah, exactly. If Z is a zero object in C, then Z is an initial and a terminal. By the way, terminal objects are also called final objects, but I don't like that name. And terminal object in C, which implies, as we just now saw, Z is a terminal and initial object in C op, which implies Z is a zero object in C op. Understood, right? So Z is initial, so it will become terminal in C op. Z was terminal as well in C, so it will become initial in C op. So Z is again both initial and terminal, so Z will be a zero object. I don't know why the writing has stopped all of a sudden. Yeah. So C is true. And what about D? D says that if C has an initial object A, a terminal object B, and a zero object Z, then A is isomorphic to B, which is isomorphic to Z in C. The screen, should be true, right? We have already seen that any two initial objects are isomorphic. By duality principle, any two terminal objects are also isomorphic. Now, if A is an initial object in C, Z is a terminal object, then A is isomorphic to Z because Z in particular is an initial object. Similarly, if B is an initial object, B is a terminal object and Z is the zero object, Z being terminal implies that B is isomorphic to Z. So the equivalence nature of isomorphism, equivalence relation nature of isomorphism guarantees that A is isomorphic to B is isomorphic to Z in C. So D is true by the argument in A, option A. Okay. Okay, so we have solved one problem at least. Let's quickly move on. Yeah, so the questions are pretty simple this week, and in fact they will be simple for some time, for some weeks at least, and hopefully for all the weeks. But yeah, let's quickly look at question 2. I don't know why the screen keeps yeah, so this is question 2. So let X be a poset, that is a partially ordered set, and you consider the category script X defined as follows. So we already gave an example of this category, right? We already saw what this category is. The objects of X are the elements of X. The Hom set from A to B in X will be a singleton if A is less than equal to B in X, and it will be empty otherwise. So there is exactly one arrow from A to B if and only if A less than equal to B, and there are no arrows from A to B otherwise. Composition is just the transitivity of the partial order, and identities are just the reflexivity of the partial order. Now state whether each of the following statements is true or false. So first is, an initial object of X, if it exists, is the least element of X if it exists. Is this true or false?
True.
It should be true, right? By the very definition, it should be true. So let's quickly write it. So A is true. I'm sorry if the writing is not appearing at the same time. I'm in real time, but yeah. So A should be true, and why exactly is that? If I is an initial object, let's write the objects by small letters. If I is an initial object of X, then for every object little x in X, there exists a unique arrow from I to X, which implies that for every object X in X, in the partially ordered set X, for every element X in the partially ordered set X, I is less than equal to X, which implies that I is the least element of the partially ordered set X less than equal to. Okay, so this is just an instance where category theory sort of helps order theory, right? Using the category theoretic properties of your category script X, you are inferring something about the order theoretic properties of your partially ordered set X. Okay, so question B, X has a zero object if and only if X is a singleton. What do you think?
True.
It's true. Why?
The anti-symmetry prevents any other case.
Okay. So, give me a slightly more defined argument.
So if X is less than Y and Y is less than X, then X must be equal to Y.
Yeah, that's the anti-symmetry. But why does having a zero object mean that X is singleton?
So zero object will have arrows both from the zero object to some other object and from some other object to the zero object.
Exactly. So basically X has a zero object means that object is both initial and terminal. initial object, as we have just seen, is the least element of X. A terminal object, as you can easily verify, will be that greatest element of X. And what this says, what a particular object being a zero object means, is that it is both the least element as well as the greatest element, which can only be possible if and only if there is exactly one element. So option B is true. Okay. If Z is a zero object X, by part A, Z is the least element of X as well as the greatest element of X. So for all elements little x in X, Z is less than equal to X is less than equal to Z, which implies that X must be equal to Z by antisymmetry of the partial order. So X has exactly one element, and the converse is obviously true. If X has exactly one element, then that element considered as an object of the category script X will be the zero object. Converse is true. So there is nothing obvious. I don't like writing this word, but for the in the best interest of time, converse is obviously true. Yeah. Again, the writing is sort of frozen. Yeah.
No, it's clear. It's coming
Okay.
in real time.
Okay. So the next question says, if little x is isomorphic to little y in the category script X. So little x is an element of your partially ordered set X considered as an object in the category script X. Same as for little y. So if little x is isomorphic to little y in script X, then X must be equal to y. Is this true or false?
True.
It should be true, right? Obvious. Again by antisymmetry. It's true. If little x is isomorphic to little y in script X, by definition this means that there exists an isomorphism from little x to little y, right? So let's call this isomorphism to be F. Now this is an isomorphism, implies that there exists another arrow G from y into x, little y into little x in script X, such that G composed F is 1x, 1 little x, F composed G is 1 little y. We are doing everything inside the partially ordered set X considered as a category script X. Now having an arrow, we are having something more than an arrow. I mean, we are having an arrow with a special algebraic property, namely an arrow which is an isomorphism here. But just having an arrow from x to y means that x is less than equal to y. So x less than equal to y, and having an arrow from y to x means that y is less than equal to x, which by antisymmetry of the partial order means that x is equal to y, which is exactly what we have. So such a category is called a skeletal category. So let me make this definition. A category, so this is a general remark or a definition. A category script C is called a skeletal category if it has no two isomorphic objects which are distinct. Of course, every object is isomorphic to itself. So note that if A is an object in a category, then the identity map from A to A has this property that this is invertible. So in the sense that there is another arrow in the opposite direction, which when, namely the identity itself, which when composed with identity gives you identity. by definition of, by the identity axiom. So identity arrow from A to A has this special property that it is invertible. It's an isomorphism. Okay, so every object A is isomorphic to itself. That is always true in any category. But a category C is called skeletal if there are no two distinct isomorphic objects. So what I mean by this is, if A is isomorphic to B as objects in C implies that A is equal to B. And a poset considered as a category is a skeletal category. Okay. Yeah. So option C is true. What about option D? X is thin. Okay, so we also need to mention what thin category is. Okay, so again this was defined. I probably the instructor used the term pre-order. One can also call it a thin category. So a category C is called thin if for every ordered pair of objects A comma B in C, cardinality of the Hom set in C from A to B is less than equal to 1. That is, in other words, a category C is called thin if for every ordered pair of objects in the category, let's say A is an object, B is an object, there is there is at most one arrow from A to B. This is what a thin category is. Okay. So let this writing come. I'll ask you some examples and we can proceed. It's still not showing. Yeah, so a category C is called thin if for every ordered pair A comma B of objects of C there is at most one arrow from A to B. That is, the cardinality of the Hom set in C from A to B is less than equal to 1. So tell me, is this a thin category? Category with 3 objects and there are exactly the identity arrows. Wait, I don't know why. Yeah, let the writing show up.
So yes, it's showing so.
Sorry.
It's showing.
Okay, it is showing. Yeah. So is this a thin category? Category with exactly 3 objects and exactly 3 arrows which are just the identity arrows.
I think yes.
Yes, because for every ordered pair of objects, in particular if you take, let's say this object is little a, this is little b, this is little c, then little a comma little a, the Hom set from little a to little a in particular has exactly one element which is the identity on A. Its cardinality is less than equal to 1. Similarly, the Hom set for B, the Hom set from B to B, the Hom set from C to C, the Hom set from A to B, which is empty here, has cardinality less than equal to 1. So everything has cardinality less than equal to 1, which means this is a thin category. Tell me, is this a thin category? Suppose the objects are the same. Now I add an arrow from A to B. Is this a thin category?
Yes.
Again, yes. Is this a thin category? I add one more arrow from A to B.
No.
This is not a thin category. Is this a thin category? So A to B there is an arrow, B to C there is an arrow. You also have composition, which means to this pair of arrows there should be assigned an arrow from A to C. So is this a thin category?
Yes.
This is a thin category, right? Because I am saying that if this is F, this is G composed F. So there is exactly one arrow from A to C which is G composed F. Right? Is this a thin category? So there is one more arrow from B to B, which is not the identity. Is this a thin category?
No.
This is not a thin category. Okay, so understood. A category. So here is what comes from, someone commented that we shouldn't say the Hom set is a set. We should call it a class. And that is what makes this new definition. A category C is called locally small if every Hom set is a set. If every Hom set of the category is a set, we call it a locally small category. That is, in other words, there is exactly a set worth of arrows from A to B for every ordered pair A comma B of objects of the category. There is exactly a set worth of maps from A to B. That is a set worth of morphisms from A to B. Okay. If each Hom set is a set, then we call it a locally small category. Now, you might ask what.
Explain it a little.
Sorry.
Could you explain this at a little? Means home set is a set. It should be a set, right?
No, the name is Hom set, but it's not a set. In our definition, we assume that it is a class. If you can see, where was it written?
Yes, and initially we have taken it's a class.
Yeah. So we want this class to be a set itself. So of course you might ask what exactly is the difference between a class and a set. So the idea is there are various, so set theorists can answer this question better, but the idea is that there are various different models of set theory. You can choose any one particular model of your liking, and every such model will give you a distinguishing, will distinguish between sets and classes. So think of a set as, think of a class as a big set, something which doesn't really qualify, something which is too big to qualify as a set. That is what a class is. So there are various ways of understanding this. There are various axioms. There is this Grothendieck universes axiom, which is some kind of a large cardinals axiom. You can take, for example, the simplest way to do this is the Gödel-Bernays theory. Okay, where did I write this? Yeah, so we won't be focused much on set theoretic issues, size issues, but the Gödel-Bernays theory says that, so in set theory you have two primitive notions: the notion of a set, you don't actually define what a set is, and the notion of belonging, an element belongs to a set, is also a primitive notion. In Gödel-Bernays theory, besides these two theories, you have three primitive notions: set, in total you have three primitive notions: set, elementship, that is belonging, and class. So think of a class as a big set. So it's not a set actually, it is too big to qualify as a set. And what exactly distinguishes between class and set? This is your axiom, which says that every set is a class is a set if and only if it belongs to some other class. So whenever a class belongs to, as an element, whenever a class is a member of some other class, we'll classify it to be a set, we'll call it to be a set. Okay, this is what distinguishes. So a class which does not belong to any other class will be called a proper class. So as an example, I'm pretty sure you have seen this previously, there is something called the Russell's paradox, right, which says that the class of all sets is not a set. In the sense, if you collect all the sets together and take that particular class, it is too big to qualify as a set. It is a proper class. Okay, if you haven't seen, please do have a look. And this was like one of the initial issues with naive set theory, which is why axiomatic set theory came into the picture. And this was sort of this paradox was sort of avoided by using the axiom of substitution. Just have a look, just wiki it. Yeah, so this is what a locally small category is. Local means at the Hom set level. So a category C is called locally small if each Hom set is a set, and a category is called small if it is locally small and it has a and the class of objects is a set. In other words, So let's just write this definition. A category C is called small if the class of all morphisms that is arrows, that is maps, is a set. So what is the class of all arrows in the category? It's exactly the disjoint union of C, A, comma B's, right? Where the ordered pair A, comma B is in object C cross object C. This is the class of all morphisms, that is the class of all arrows, that is the class of all maps in the category. We call the category to be small if this class is a set, if the class of all morphisms is a set. And note that since you have this canonical map, in fact embedding from objects of C into arrows of C, the class of all arrows, which sends any object A to the identity arrow on A. This is a well defined map, no issues about that. And this is injective as well, right? Obviously, because if identity on A and identity on B agree, then it better be that A and B agree themselves, right? It's because every arrow has a unique domain and a unique codomain. Every arrow has a unique source, that is domain, and a unique codomain, that is target. So if 1A and 1B are equal, that means in particular that A and B have to be equal. So this is an injective mapping. So the class of all objects can be embedded in terms of injective map into the class of all arrows. Now if you assume that the class of all arrows is a set, this kind of, by using some more axioms of Gödel-Bernays theory or whatever your favorite set theory is, also implies that the class of all objects is a set. So it is enough to say that the class of all morphisms is a set. And this is also equivalent to saying that C is locally small, that is each Hom set is a set, and OBC, the class of all objects of C, is a set. Okay, enough definitions for now. Let's quickly jump. Yeah, by the way, example, we should also mention an example. So example, the category set is not small because the class of all sets is not a set. The category X corresponding to a partially ordered set X less than equal to. So a single partially ordered set X less than equal to is being treated as a category, as we saw in our previous problem, or in one of the examples that we mentioned. Wait, let the writing come up, otherwise you'll get confused. I don't know why this is stuck. You guys can't see the example, right?
We can see it is written set is non-empty, X is corresponding to the full set.
Okay. So X, okay. So the partially ordered, the category X corresponding to the partially ordered set X, as we mentioned in one of the examples, is small because the class of all objects of the category script X is exactly the set capital X, and it is a thin category in the sense that there is exactly one, there is at most one arrow from one object to another object, which means that it's a small category. Okay, so coming back to our question, I hope problem 2 was done. Yeah. Oh no, problem 2, one was left. So option D says that our category script X corresponding to the partially ordered set X less than equal to is thin, locally small but not small. Is this true or false? Is this true or false? So X is X a thin category or not? Is cryptex a thin category or not?
Yes.
It is, right? Because for every ordered pair of objects, there is at most one arrow from the first object to the second object, right? So if the first object as an element of the partially ordered set is less than equal to the second object, there will be exactly one arrow. Otherwise, there will be no arrows. So there is at most one arrow. So it's a thin category. Is it locally small? Each home set consists of either 0 or 1 elements, right? So each home set is a set.
Yes.
And is it, again, we haven't really mentioned that having, finite sets qualify as sets themselves in our Gödel-Bernays theory, but use your intuition here. And is this a small category? We already mentioned it is, right? Because
Yes.
it is locally small and the class of all objects is small. A set. So option D is correct, is true. Statement D is true. Already considered. Okay, let's move on. Let us finish problem 3 at least, then we can stop. So state whether the following statements are true or false. A category C is thin if and only if all diagrams in C commute. You guys know what a commutative diagram in a category is, right?
I don't. Sorry.
Okay. So a diagram of objects and arrows in a category C is called commutative if any two sequences or directed paths, let's say, paths of arrows in C with the same starting object and with the same ending object yield equal arrows upon composition. So it's a very natural definition, very natural to expect. So assume you are inside a category and assume you have taken an object A, let's write it as a dot, an object B, an object C, an object D, and suppose you have arrows like this. Let's call this F, this is G, this is H, this is E, let's say. So question is, when do I say that such a diagram is a commutative diagram? So by this I mean that if you take any two sequences of arrows, for example, if you take this sequence and if you take this sequence, these are two sequences which have the same starting object, which is this black dot at the top left corner, and these two sequences have the same ending object, which is this dot at the right corner, bottom right corner, then of course this means that if you compose this particular sequence FG, you should get an arrow from the dot at the top left corner to the dot at the bottom right corner, and if you compose the second sequence HE, you should get an arrow again from dot in the top left corner to dot in the bottom right corner, right? It is natural to expect that these two arrows should be equal because they are parallel arrows. We can compare them. I mean, these two arrows have the same domain object, that is the source object, and the same target object, that is the codomain object. So it is natural to expect that these two arrows should be equal. If they are indeed equal, then I'll say that the diagram is commutative. So I'll say that a diagram of objects and arrows in a category C is called commutative if any two directed paths of arrows in the category, in the diagram. We are talking about the diagram, not in the category. In the diagram, with the same starting object and with the same ending object lead to the same arrow upon composition. So for example, as I already mentioned, composing this sequence gives you an arrow G composed F, and composing this sequence gives you an arrow H composed D. Saying that the diagram is commutative means that these two arrows are equal. Okay, so tell me, so saying that this is commutative means that G composed F is equal to H composed D. So now let me give you one more diagram. Suppose this is your diagram. This is F, G, H, J, K, L, M. What do I mean when I say that this diagram is commutative? So what are, you have to identify pairs of sequences which have the same starting object and which have the same ending object.
So it could be any of like H of G of F equal to J of L of F equal to J of K of M.
Okay, so you have identified first of all three different sequences. This is one sequence whose starting object is this dot, ending object is this dot. You have identified this sequence. Oops, sorry, what was the other sequence? Yeah, you have identified, okay.
To L.
Yeah, so this is one sequence, this is another sequence, again with the same starting object and with the same ending object, and this is another sequence, again with the same starting object and with the same ending object. So you want H composed G composed F is equal to J composed L composed F is equal to J composed K composed M. What else? You also have this sequence, right? This is also a sequence. I mean, these are also two different sequences with the same starting object and with the same ending object.
We can take any two, right? Like L of F equal to K of M and H of G equal to J of L.
Yeah, so now you consider this sequence and you consider this sequence. Again, these are two sequences with the same starting object and the same ending object. So H composed G is J composed L. I guess that's all. Yeah, that's all. So this is what it means for this diagram to commute. One final question. Or maybe two more final questions. Suppose you take a diagram like this. What do I mean by this diagram? By saying that this diagram is commutative or this diagram commutes? So let's A, B, C, D, E, F. Yeah.
I can say D of C of B of A equals to E of F.
Yeah, and there are no other two sequences of arrows with the same starting object and with the same ending object. These are the only two such sequences. Yeah, exactly. When a diagram commutes, you usually write something like this, a hash symbol in the middle of the diagram, or something like a circular arrow to indicate that the diagram is commutative. There are non-commutative diagrams, obviously. So to distinguish them from commutative ones, we write commutative diagrams we decorate them with a circular arrow in the middle. Yeah, what do I mean by saying that this triangle commutes? F, G, H. So identify the sequences first of all.
So we can say h of f equals to z.
Yeah, exactly. So this is one sequence whose starting object is this, ending object is this, and this is another sequence having exactly one arrow whose starting object is this, ending object is this. Being commutative means that the two sequences should give equal arrows upon composition. So what you want is H compose F is G. This is what it means that the diagram is commutative. Final question. FG. What do I mean by saying that this diagram is commutative?
F equals to g.
Exactly. So you have two sequences. One is this, another is this. Both sequences have exactly one arrow. Now, and both sequences have starting object this and ending object this. So saying that the diagram commutes means that F should be equal to G. Right. So the question says a category C is thin if and only if all diagrams in C commute. Is this true or false?
Should be true, I think.
Should be true. So what about the forward direction? If C is thin, do all diagrams in C commute?
Yeah, that's due to composition law.
Be precise, please. What do you mean by composition law?
So there is only one arrow
Exactly,
between
exactly.
at max one arrow between two objects. So
Exactly.
f of g will be the arrow between the
So if you take a
composition of
diagram
f.
where you can raise a question of commutativity, which means you have at least two sequences in the diagram, you pick any two sequences in the diagram with the same starting object and with the same ending object. Composing one sequence gives you one arrow from the starting object to the ending object. Composing another sequence gives you another arrow. And the category is thin, which means there is at most one arrow from the starting object to the ending object, which means these two arrows must be equal. So correct, absolutely correct. A. So if C is thin, all diagrams in C will commute. So let's just write obvious. And what about the converse direction? If all diagrams in C will commute, does that mean C is thin?
If all diagrams commute, then you can, for two morphisms f and g between A and B, you can commute them with the identity function to show they are equal.
No need to, what do you mean by compare them with the identity function?
Sorry, compose them with the identity function.
No need to compose them with identity function. I mean, just taking two arrows is enough. So conversely, if C, so this is how we prove the converse one. I mean, it's just a trivial argument, but let's just write it properly. If C is not thin, there exists two arrows F and G which are different from an object A to an object B, which contradicts the commutativity of the diagram. Because we just saw saying that this diagram is commutative means that F should be equal to G, because F and G are two different sequences of arrows consisting of exactly one arrow each, such that these two sequences have the same starting object and they have the same ending object. So saying that this diagram commutes means that the compositions given by each sequence should be equal. So the first sequence consists of exactly one arrow, which is F, composes to give you the arrow F. The second sequence consisting of exactly one arrow G composes to give you the arrow G. So saying that this commutes means that F should be equal to G, which is not the case here, which therefore contradicts the commutativity of this diagram. Okay, let's consider part B. Okay, so statement is true. So A is true. What about part B? Part B says if an arrow F from A to B in a category C is an isomorphism, then the corresponding arrow F of from B to A in C op is an isomorphism. Is this true or false?
True.
It should be true. So B is true if F from A to B is an arrow in C is an isomorphism in C. This implies that there exists an arrow G from B to A in C such that G composed F is 1A and F composed G is 1B. By the way, we are sometimes denoting objects by capital letters and sometimes denoting objects by small letters. Yeah. So this holds, which implies that in the opposite category C op, F op from B to A, the corresponding arrow corresponding to F, has the property that there exists an arrow G op. Because G exists in C, G op exists in C op. So G op exists in C op and G op has direction A to B in C op such that if op composed with G op, which was defined in the definition of composition law of your of the opposite category of a category, this was defined to be G composed F op, which is 1A op, which is the identity on the object A in the opposite category, and G op composed F op is F composed G op, which is equal to 1B op, which is the identity arrow on the object B in the opposite category, which implies that F op, this arrow, is actually has the special algebraic property of being invertible. That is an isomorphism. So was this a if and only if statement? Okay, then. By the way, if and only if is true, right? Because if C is a category, if you take its opposite category C op, and if you then again take the opposite category C, so C op, that is just C. So the converse is also true. If F op is an isomorphism in C op, then F will be an isomorphism in C. Right. Okay. I guess we'll stop here. We have to stop here. We'll solve. Are you guys free for 10 more minutes?
Yes, fine.
Okay, so let's at least finish this problem. So I haven't really defined what a groupoid is, but you can understand what it should be. So a bit more theory. Again, this is all assuming that the lecture notes, lecture video has not been, you haven't seen the lecture videos, but please do see them before attending the tutorial on Fridays, because it is very difficult to mention theory and as well as solve problems. We'll only be solving problems in the tutorial sessions. If you have any questions, you can email me, and doubts you can ask me, but of course please do have a look at the lecture videos. Yeah, so so do you know what a monoid is? Do you know what a monoid is? You know,
A monad is a monoid in the category of endofunctors.
no, that's a monad. I'm asking about a monoid, ordinary monoid.
The binary operation is only associative and identity is there.
Exists, yeah. So it's just a set together with a binary operation which is associative and has an identity element. This is what a monoid is. So what we plan to do is think of a monoid as an abstract category, but with exactly one single object. So consider the category script M defined as follows. So exactly script M has exactly one object, whatever it is. We can just use any symbol for it. It's just an abstract object. We don't care what is it or whether it has any internal data or not. As I mean, we are continuing with the philosophy of category theory. No internal structure of objects. So it has exactly one object, which we'll write, let's say, by star. Okay. And what is the there? We have only one home set, namely the home set from star to star. So the home set from star to star in script M will exactly be my monoid M. In other words, what I am saying is the elements of the monoid are being treated as arrows from star to star. So if little m is in capital M, then little m is being thought as an arrow from star to star. This is what we mean. Okay. So all arrows from star to star are precisely all the elements of M. What is your binary operation? What is your composition? So if you take an arrow from star to star and another arrow from star to star, let's say this is M, which is an element of capital M. This is M prime, which is another element of capital M. Well, how can I define this composite arrow from star to star? What do you think? M was a monoid. It has a binary operation. So we can just define it to be the arrow M prime M. So we define M prime composed with M as arrows in your category script M to be exactly M prime times M as elements of the monoid. Of course, M prime times M is an element of the monoid M. So it will again be an arrow from star to star, and that is the arrow, that is our third arrow that we assign to the pair M comma M prime of arrows in your category. Okay? Is this clear? Is this clear?
I have a question.
Yeah.
So we are taking the elements from the monoid, right?
Yeah.
So when we're taking this arrow from star to star, there is one object. So there can be multiple arrows.
Yeah, there are multiple arrows. That is what this means, right? This line says that
Okay.
all the set of all arrows from star to star is exactly the set M. So
Okay.
if your monoid is, so as a concrete example, if Z is your monoid, then the corresponding category will have one object. Let's say box is your object. Box is the only object, and all the arrows from box to box will be all the elements of Z. So 0 is an arrow, 1 is an arrow, -1 is an arrow, 2 is an arrow, and so on. Okay.
Okay.
So in particular, this is not a thin category. Yeah, so this is how composition is defined. Composition is associative precisely because multiplication or binary operation of the monoid is associative. And what should the identity element be? What should one star be? As an arrow from star to star, that is, it should in particular be an element of M. What element can we take?
The identity
The
element.
identity element. Identity element. There is exactly one object, so there is exactly one identity arrow. And the identity arrow is exactly the identity element of the monoid. So this is again an abstract category, right? So my point is, a monoid can be seen as a category with exactly one object, as we have seen here. Conversely, every category with exactly one object is a monoid. This you can verify in the sense, so what is your operation? So the category should have exactly one object. Let's say the object is question mark, let's say. So there is exactly one object, means that there is exactly one home set, and this home set actually has an algebraic structure of composition, because composition is a map from this cross this into this. So it's a binary operation essentially. right? So that means that this is a binary operation. Composition is associative. It's a semi-group therefore, and composition has an identity element, namely the identity arrow on this single object, which makes it into a monoid. So a category with exactly one object, or a small category with exactly one object, is the same thing as a monoid. Now, you all of you know what a group is, right?
Yes.
So what is a group? A group is a monoid in which every element has an inverse, right?
Yes.
Now a monoid is a category with exactly one element, exactly one object, and a group is in particular a monoid. So a group can also be considered as a category with one object, right? So what I'm saying is, since a group G is a monoid in particular, yeah, since a group G is a monoid in particular, the above construction can also be applied to the group G. Because a group is in particular a monoid. A monoid with extra property which is in asking for invertibility of every element of the monoid. So the group G is a monoid in particular. So we can apply the above construction to get a category G which has exactly one object, which is star. And what is the Hom set? So G from star to star, as was defined in the monoid case, is exactly G, the group G. So the elements of the group are being regarded as arrows from star to star. The composition is given by multiplication in the group G. So this is a category with exactly one object, but this category in fact has a very special property. So since the group is a monoid with a special property, the corresponding category should be a special category. It should have a special property. What is the property? Can you guess?
All isomorphisms.
Isomorphism.
Yeah, all arrows are isomorphisms, right? That is what you mean, right, Advay?
Yes.
Yeah, all the arrows are isomorphisms. So if G is an arrow from star to star in the category G, then this arrow G actually has an inverse. It is invertible. What is the inverse? G inverse, which is also an element of G, star to star. If you compose them, you get the identity arrows by our definition of composition. So this G is a special category. It is first of all a category with a single object, that's okay. But this category has this special property that every arrow is an isomorphism, right? So a group, and conversely, if you take a small category with exactly one object in which every arrow is an isomorphism, then that will exactly be a group. Okay. So now we make this definition. We generalize this, and this is again a very common theme in category theory, something called oidification, which sort of first of all studies categories. Which sort of is a way of replacing algebraic structures by categories with exactly one object, and then by studying such categories in general. Such special categories in general, in the sense that now the categories can have many objects. So I'll say that a category C with many objects, any number, the class of objects can be anything. A category C is called a groupoid if every arrow in C is an isomorphism. Pretty simple, right? So a category C is called a groupoid if every arrow in C is an isomorphism. In other words, a category C is called a groupoid if every arrow in C is invertible. And a single object groupoid, that is a groupoid with a single object, is a group. Exactly. So a groupoid with a single object will be a group. Exactly. So let's quickly, I hope the definition has been understood. Let's quickly get to the next two statements. We'll then stop. So the category set inj, whose objects are sets, morphisms are injective set maps with usual composition and identities, is a groupoid. Is this true or false? First of all, tell me, is the category set a groupoid? I mean, the arrows in the category are maps, set maps. Set maps. Is the category of sets and set maps a groupoid?
No.
No, right?
No.
Because if it were a groupoid, then every arrow should be an isomorphism. Translated to the particular example of sets, I mean the category of sets, this would mean that every map should be bijective, which is obvious nonsense, right? So not all arrows in the category of sets are invertible. So the category set is not a groupoid. Now the question is sort of is taking a subcategory of the category of sets. It's a wide subcategory in the sense that all the objects are being taken. So I mean all sets are being taken, and now the arrows are just injective set maps. So earlier in the category of sets, you had a map from, let's say, AB to C, but now you don't have any map from, in this new category set inj, there is no map from AB to C. No such arrow exists. Okay, this is what set inj is. You just only takes injective maps. So question is this a groupoid?
No.
This is not a groupoid, right? Can you prove this? First of all, what is an isomorphism in this category?
Sorry?
In set inj, what would an isomorphism look like?
Injective maps that composed give identity.
Okay, so what are those exactly?
Bijective maps.
Exactly. Because if you have an injective map in set inj, so let's write it properly and quickly. So C is false. If F from A to B, here we are again using capital letters to denote objects. We could also use small letters. If F from A to B is an arrow in set inj, which is an isomorphism, by definition this means that there exists an arrow G from B to A in set inj such that G composed F is 1A and F composed G is 1A. Note that, by the way, this became set inj is a category because composition of injective maps is injective and identity map itself being bijective is injective. So this is a perfect category. Set inj is a well-defined category, and an arrow is an isomorphism means that there is an arrow in the opposite direction which satisfies this. Now F is an arrow in set inj in particular means F is injective. G is an arrow in set inj means in particular G is injective, and hence we want G composed F is identity on A, F composed G is identity on B. This holds in the category set inj, and since compositions in the category set inj are exactly given by compositions in the category set, usual composition, this implies that F is bijective regardless of whether it was initially assumed to be injective or not. So this implies that F is bijective. So for F to be, F is bijective as a map in the sense of set theory. F is bijective. I mean bijective only applies in set theory. So F is an isomorphism in category theory in the category of set, in the category set inj, implies that F is bijective in the category I mean as a map of sets, right? So, and conversely, if F is bijective as a map of sets, then of course F will be an isomorphism in set inj. So set inj is a very particular subcategory of set consisting of all the isomorphisms, and no new isomorphisms are being created in set eng. So the point is, I mean, what I want to say ultimately is that set eng is not a groupoid, because there are injective maps which are not surjective. Final question: if G is a group considered as a category with a single object, which is exactly what we did in the previous example, we generated an abstract category with a single abstract object, and the arrows are the elements of the group, so abstract arrows. I mean arrow, yeah. So that category that we gave as an example, so say it says that this category has a terminal object. Is this true or false?
Who was this in the single set only?
Sorry.
It's true.
Okay, so let me read the question again. If G is a group considered as a category with a single object, so there is exactly one abstract object, and the abstract arrows of the category are exactly the elements of your group. This category will have a terminal object. Is this true or false?
If G is trivial, then it's true. Otherwise, it's false.
Correct. Correct. This is, yes. Correct. Absolutely correct. If G is non-trivial, then there are of course more than one arrows from the single object to itself. So G having since there is exactly one object, G having a terminal object would mean that the terminal object is that particular single object of the category. So that object being terminal in particular implies that there is exactly one arrow. There should exactly be one arrow from the object to itself, which is not the case if G is non-trivial. So option D is false. If cardinality of G is greater than 1, then there exist two arrows, at least two arrows from the single object to itself, right? This is some element of the group G, this is an element of the group G, right? So there exist at least two arrows. So star cannot be, since this is the only object of the category, so the category having a terminal object would in particular imply that this object is the terminal object. But and star being terminal object means that there is exactly one arrow from any object of the category to star. In particular, there is exactly one arrow from star to star. Star is the only object, we did not consider anything else. So there should be exactly one arrow from star to star, which is clearly not the case here. So star cannot be a terminal object. The uniqueness part in any universal property is very important. We are asking for a unique arrow from any object to star. This uniqueness assumption or uniqueness part is very important. So star is an object is a terminal object if and only for any object A of the category there is a unique arrow from A to that particular object, the terminal object. Yeah, so star cannot be a terminal object, and we are done. Okay, there were some other very interesting questions. We'll solve them next day, probably. If we are not, we'll see how we'll get to all these problems. But yeah, that's it for today. Any questions you can ask me, or you can email me, or you can write in the discussion forum. Yeah, that's all. Thank you. See you next week.
sir. Any
Yeah.
important instructions you gave? Because I was away for like a few
So
minutes.
so there is like a, I mean, this entire lecture is being recorded, so
Okay.
and the link will be uploaded. I forgot to record the first 10 minutes, but that was essentially motivation for category
Uh,
theory. I didn't discuss
uh,
any technical details. Okay, and by the way, you mentioned, I think you only mentioned, right, a monad.
yes.
So have you studied what a monad is?
No. I watched a few category theory videos on
I
YouTube,
see.
so that's what inspired me to take up this.
I see. I see. So a monad is a monoid in the monoidal category. The monoidal category part is very important. We'll get to that in a few weeks. But yeah, it is a monoid in the monoidal category of endofunctors on a category. But yeah,
Okay.
that's it for today. Thank you.
Okay.
Yeah,
Where can we access the recordings?
I'll provide the links. NPTEL will probably share them with you guys.
In the mail or the announcements, right?
I think please do check both. I am not sure. I have never attended an NPTEL course, but probably please do look in both places.
Okay, sir.
Okay, yeah.
And we'll have this weekly, right?
We'll sit weekly every week, Friday 6 to 8 p.m.
Sure.
Okay. See you.